Alright guys, I'm going to do a quick lecture on where we should be with telescopes in our telescope chapter, but I want to quickly go over what you should have had for your Challenger video questions. So why don't you pull those out, pause this video and pull them out so you can make sure you've got the right answers so you can turn those in. Alright, so this is the first one. If you want to pause and just make sure that you've got all of the first one finished. Alright, now the second one. Oop. Alright, here's the second one's answers, so go ahead and pause and fill those in if you missed any. Alright, the third one. Here they are. Go ahead and pause. Make sure you've got those filled in. Alright, and let's do the fourth one. Here it is. Go ahead and pause and make sure you've got those filled in. Alright, so the point of watching that is understanding that space travel in general is incredibly risky, and a lot of times we are made to believe it is not as risky as we thought. There were two huge failures in the NASA space program, and I will talk about both of those. Obviously, we should know by now that the Challenger was one, and the Challenger failed on launch, whereas Columbia failed on reentry. So I'll show you a little bit on each of those, and we'll also talk about how all of the information that we have from satellites currently is being given to us by the fact that there was some shuttle that had taken that satellite into space to begin with. So we have satellites in space, as you saw in your bell ringer, that also capture a lot of information about distant galaxies. So the James Webb Space Telescope and the Hubble. The Hubble is the original space telescope from the United States, and the James Webb is our current. Both of those are operated and maintained and data collected by NASA. There are a few other space telescopes out there, but those two actually collect and absorb an amount of a lot of energy information. Now, the James Webb was eventually intended to replace the Hubble Space Telescope, but they are both currently in orbit and in function. They both have different orbital patterns, whereas the James Webb is able to reach further into the universe, whereas the Hubble is a little bit closer to Earth. They also have different spectral images. The visual here on your screen is, remember, the electromagnetic spectrum, which we've talked about. Remember, every part of this spectrum has a specific frequency and wavelength associated with it. As you go up in frequency, you also go up in the amount of energy. Now, this visual is flipped around from what I normally show you. Typically, I show you in like Roy G. Biv, right? It starts with red on the left and ends with violet, because that's how we think of the rainbow, but also usually the EM spectrum is ordered based on increasing energy. Now, for astronomy, a lot of times they will organize it this way because for an astronomer, their goal is to reach the depths of the universe as far as they can. And so they're going to order it based on increasing wavelength, which is the inverse of increasing frequency. So they want to see how far can we get these EM wavelengths to reach. So the AM, FM spectrum you see here, so like FM radio, AM radio, and shortwave and TV here. These AM wavelengths are actually used a lot of times to gather information from the depths of the universe. I'll show you some satellites that we utilize currently to do that. Now, remember the properties of a wave. The frequency is essentially how many waves are going to pass per second. So think if you're standing on the shore of the ocean, how many wave crests were to hit you every second. And then that unit is typically described in hertz, capital H, lowercase c. You've probably heard of that before. It just is one easy way to describe how much energy is associated with that particular waveform. It is also a lot of times used to describe pitch when we're talking about sound. So frequency is the quantifiable value for the perception of sound. Pitch. Wavelength is how far it is from one wave to the next, and you have to pick one specific point on a wave, so like crest to crest or trough to trough. That way you get a full cycle. And we measure that in meters. Amplitude is essentially how far from its resting position is it. So like the center to the peak or the center to the trough. The trough is the lowest point and the crest is the highest point. Now remember that frequency and wavelength are the reciprocals of each other. So think of it as like, again, on the ocean, if you're standing there, a lot of waves hit you per second, then the distance between them is shorter. Whereas if the distance between them is longer, the frequency would be less often. Visual. All right, we've talked about a lot of this. I'm going to kind of speed around here a little bit. We did that one as well. Yes, we did. We've also done this. All right, so you should have filled out your types of telescopes graphic organizer. That video you watched yesterday with the Edpuzzle would have been a really awesome time to get that. But remember, the ones that we really have focused on are reflecting. And that, remember, reflection, think mirror, refracting, when you bend the light. Remember, I think of it like the really cute penguins at the zoo, RE for really. When the light goes through a new medium, so when we see light, it's typically just going through air. But when you look through glass, it can bend, and if you look through water, it can bend. And those are what you call refraction. The light waves are being refracted, so that's what a refracting telescope is. Think when you were looking at the lenses and you had the concave, which was like a cave, like it's pushed in, or convex, like bowed out at you. Those different bends and the curvatures and the sizes all impact how that light is going to be refracted, and that's what a refraction telescope uses. Again, reflection is mirrors, kind of like that big black telescope we used. It just had two mirrors. It was a lot harder to focus, but you can make it look like it was closer. And a catadioptric telescope takes both of these and uses them together. Now, a radio telescope just uses radio waves. I'll show you some examples. We have a lot of them currently, especially over in California. They have a lot that are set up. And space telescopes like the James Webb and the Hubble. All right, the first telescope was an optical telescope, and it was in Europe in the late 16th century. Now, there's a lot of back and forth on this because obviously anybody could take a tube and put some mirrors or lenses in it and play with it, so it had to be actually documented. Remember, think back, the internet didn't exist, so documenting took a lot more effort. Usually took publishing textbooks to tell people how to do it, which were barely done in the 16th century. So some of the first ones used two lenses, and when you put them at a certain distance apart based on their curvature, you're able to see the objects looking like they are closer. And sometimes you can make them look larger based on which lenses you use. Now, the Italian scientist and mathematician Galileo Galilei is most notably known for his telescope. In 1608, he made his very first and utilized it to do a lot of research on the stars and on planets, and especially the moon. He is most notably known for drawing the first picture of the moon, and to this day, it is incredibly accurate down to every crater that he had drawn. I believe I have a picture of it here somewhere. If not, I believe it's in your textbook. Galileo is very well known for mapping the universe before we really understood what it was. During his time, the leading theory on how things worked in terms of the Earth, Moon, Sun system was that the Earth was at the center, and we called it the geocentric system. And Galileo studied and mapped how the stars moved around us, and he'd track specific stars and specific planets and observe their patterns, and utilized math and geometry in particular to be able to tell us that in reality the Earth was at the center. And so he was one of the first to really I'd say shout it the loudest, probably. Other people theorized and suspected, but he was the first to collect the data and pitch it to the community, and it was not widely accepted by any means, and he got a lot of flack for his beliefs based on his observations. Next came the refracting. So remember, refracting, the lenses are bending. That previous telescopes were refracting, but they got bigger is probably where I should talk about them here. The bigger the lens, the more they can actually make it larger, so you're able to see smaller things a lot easier, I should say. So you can also see things further away and make them smaller things be visible. These refracting telescopes were the most common when telescopes were first being used, and things you could see really easily back then, and even currently with the refracting telescope, are the surface on the moon. You can actually see down to the craters on the moon, and then you can see the rings around Saturn. And the largest currently in the world would be the one at the University of Chicago. We'll talk about some other like radio telescopes that are huge, but for a refracting telescope to be huge, it takes a very large amount of glass, and that's what the limiting factor usually is for these guys, because they're very, very heavy then, and they cannot be moved. So that's when you get more of the viewing buildings, and I'll show you some examples of that and what they're called. All right, reflecting. Remember, think reflecting like reflection, a mirror. So a little bit later, you have Sir Isaac Newton, who is the father of physics and calculus. He was a mathematician, scientist, and an inventor, and he utilized curved mirrors to focus light. You've probably all seen some of those videos or TikToks or Reels where they take mirrors and shine them on a certain surface, and it can like start a fire or just make a really hot spot. There's actually been some engineering fails where people built buildings and skyscrapers where all the light's reflected to one point, and it can literally melt mirrors off of vehicles, because when all of that light is put into one focal point, it's a lot of energy. So reflecting telescopes do something similar, but they have those curved mirrors. Again, think back to our lab activity where we played with those. You can actually take them and focus it to the center, find that perfect distance where you can put the focal point lined up, and you're able to very clearly see what you're trying to look at up close, even though it's very far away. And the benefit to this is it takes a lot less weight than a refracting telescope. Remember, refracting, you have to have certain curvature, so the bigger that lens gets, the thicker it has to be as well, and it can get incredibly heavy. Whereas reflecting, I'll show you an example where a guy just literally polishes a piece of glass till it's shiny, and he uses it like a mirror. Amateur astronomers use the reflecting telescopes a lot because I know for mine, for instance, it's quite heavy, and being able to move it anywhere is challenging. And if you jar it just right, they're not usable any longer. So you want to be able to transport them easily, and reflecting telescopes do that really well. They're a lot more lightweight than others. Here are some examples of reflecting telescopes. So while they're thicker here, as you can see, they are lighter weight than if that would be a lens. Now, catadioptric are a combination, and these are a lot more common now because they are lighter weight, they have a very crisp image, and they have much shorter tubes. My tube, for instance, is about almost a foot in diameter, I would say, and it is about 4.5 to 5 feet tall, and that makes it really, really hard to move. It gets a really great image, but it's hard to move. So these shorter tubes and crystal images are really, really handy. Radio telescopes capture radio waves instead of light waves. So both reflection and refraction, when we're looking at them with the naked eye, are looking at the visible light spectrum. Radio telescopes, they'll look like a satellite dish, and they're scooping up all of the radio waves that are coming in, or microwaves, and they can either collect the data, or they can actually bounce signal back as well. But in terms of telescopes, they're trying to capture it. This Arecibo Observatory in Puerto Rico was the largest. It's still there, but it's not functional any longer. It had a huge failure. I think it's like 3 years ago now. I'll show you a video clip on it, but know that it's not currently in function any longer. But it was put into a naturally occurring sinkhole, and for that reason it's not able to be moved, so they aren't upkeeping it because it would take so much to repair it. Here it is. Like I said, not in function any longer, but it was the largest observatory. The term observatory is just used for any type of telescope facility where they're observing space, or the depths of space in this case. All right, now some that are currently in function, like the Allen Telescope Array. These are a series, so a large group of radio telescopes that they put together, and they work with each other and collect data. So instead of one big one, there's a whole bunch of little ones, and they all pull their data together. So here is a little video on
Okay, imagine you're at the beach. In order to figure out if there are fish in the ocean, you dip an empty glass into the water and look inside. No fish in the glass? Well, there must be no fish in the ocean. Not too logical, is it? But that's exactly the type of reasoning that's plagued Dr. Jill Tarter for years. Astronomers like Tarter began searching for alien intelligence in our galaxy about 4 decades ago. In that 40 years, they've only managed to search 1,000 star systems, 1,000 glasses of water, while an unexplored cosmic ocean lay right in front of them.
40 years needs to be put in the context of how big the universe is, how enormous this cosmic haystack is that we're trying to search through. And so we've just begun.
Dr. Tarter knows a little something about SETI, the search for extraterrestrial intelligence. She's an astronomer and the current director of the Center for SETI Research in Mountain View, California. Tarter, like many SETI scientists, was drawn into the search by the early work of astronomer Frank Drake. Drake looked at the makeup of our galaxy and created an equation to determine the likelihood that other intelligent life exists. By factoring in variables like the fraction of stars with orbiting planets, the percentage of planets that go on to develop intelligent life, and the length of time that an intelligent race lasts, Drake's equation made it clear. Scientifically, the odds are pretty good that we are not alone. But if you're hunting for ET, where do you start? What would the sign of a technically sophisticated alien culture look like? It could look something like this. Television and radio signals like this are examples of artificially focused electromagnetic waves, and we've been leaking them into space for over 80 years. That means any planet within 80 light years of Earth is receiving them. Signals like this are simple to generate and use, and carry well over vast distances. That's why SETI scientists believe alien cultures might be leaking them just like we are. In 1979, as a young graduate student, Jill Tarter joined the hunt for these telltale signals.
I was so enthralled by the idea that I lived in the first generation ever of human beings that could try and answer the "are we alone?" question by doing an experiment rather than just asking the priests and the philosophers what they believed.
By the early 1990s, with NASA funding, Tarter was heading up the search at the largest facility in the world, the Arecibo Radio Telescope in Puerto Rico. Tarter became the poster child for SETI. Even Hollywood embraced her. Tarter is generally thought to be the inspiration for Ellie Arroway, the character played by Jodie Foster in the classic science fiction movie Contact. It seemed the golden age of SETI had arrived. Then, in 1993, Congress abruptly shut off all federal SETI funding. But that wasn't the end. Today, nearly 15 years later, something big is happening in this remote valley near Hat Creek, California. SETI's luck may be about to change. These radio telescope dishes signal the beginning of what many believe will be a SETI renaissance. If there is to be a breakthrough, the New Allen Telescope Array is the best bet. The reversal of SETI's fortune has largely been made possible by a $25 million grant from Paul Allen, one of the founders of Microsoft.
There we go. 1, 2, 3.
On October 11, 2007, Allen pushed the silver button, bringing the first 42 radio dishes online. When completed, the Allen Telescope Array will consist of 350 separate dishes. Together, they can operate as a single virtual dish over 2,700 feet across, making it one of the largest and most sensitive radio telescopes in the world. It will be the fastest tool ever built to hunt for signals of extraterrestrial intelligence. Senior SETI astronomer Seth Shostak tells us how this new telescope will work.
Now, clearly, we're trying to find evidence of ET, and we're trying to do that by looking for a signal in what's called the electromagnetic spectrum, which is just a fancy way of saying the radio dial, at least for us. Now, let me turn on my radio here. Okay, you hear that static, all right? That's just all natural noise. Galaxies and hot gas between the galaxies and pulsars and quasars, they all make radio noise, and it's everywhere on the dial. But if I tune a little farther here, hear that squeal, and then right there, intelligent life, okay? And that's the difference between nature and some deliberate signal, because it's at one spot on the dial. Nature does not make signals that are restricted to one spot on the dial in general. It just doesn't do that.
Since the cosmos just don't make narrow-focused signals like this, finding one would be an almost certain sign of an alien culture. So what is it about this new array that makes it more likely to succeed?
The Allen Telescope Array basically is all about speed. We can look at more than one star at once. And so, whereas in the last decade, we looked at about 1,000 stars, in the next decade, we'll look at 1 million.
That's because the Allen Array's field of view, the area of sky it sees at one time, is much larger than any other telescope. And it can capture millions of frequencies from multiple star systems simultaneously. Basically, the Allen Telescope Array is a SETI hot rod, with SETI astronomers at the controls 24/7.
So if you look inside here, you kind of see where the rubber meets the road in terms of these antennas. I mean, the operation is actually, in principle, very, very simple. The radio waves come in from the sky, and then they come down to this Buck Rogers-looking thing here. This is called the feed, but really all it does is it takes those incoming radio waves and amplifies them and turns them into electrical signals that then go down a fiber optic cable back underground to the control room. Now, this thing looks so funny because it's got to be able to pick up radio waves that are at various wavelengths from from relatively long to relatively short. So that's why it has this tapered look. The back end here is for the longer wavelengths, the front end for the shorter. The antennas send everything they collect from the cosmos into this room. That comes in right back here. You think of what Frank Drake did in 1960. He had one channel of radio noise he was monitoring. One. Here we got 100 million channels coming in, and then we move up the dial to take another 100 million and another 100 million.
The sheer scale of the search is almost impossible to imagine. Remember, in our galaxy alone, there are over 300 billion other suns, many with orbiting planets. And beyond that lie 100 billion other galaxies, just like our own. Even in its current configuration, the array's virtual dish gathers 9 times more information than present-day processor technology can decode. That means 90% of what the telescope observes is simply thrown away. So for the next decade or two, the technology in this little room will be playing catch-up with the dishes outside.
We know that technology is going to continue to advance at an exponential rate, and so all this stuff will be replaced in another 5 years by yet faster machines, which allow us to look at more star systems, more channels, in other words, to speed up the SETI search.
And as that search accelerates, Tarter and other SETI scientists are thinking about the consequences of success.
If we detect a signal, we'll do everything that we can at this site to make sure that it isn't our own technology that's fooling us, or that it isn't a deliberate hoax. If we get an independent confirmation, then we will, in fact, tell the world. Because a signal isn't being sent to the Allen Telescope Array, it's being sent to the planet Earth. And the planet Earth deserves to know about it.
But once the world has been notified, then what? Let's just say an official response plan probably won't be necessary.
If you ever announce that you've detected a signal and give the description of what it is and where it's coming from, anybody with a transmitter is going to get on the horn and shout whatever they want. And wouldn't that be just about the best characterization of 21st century Earth in an unorganized cacophony?
That's exactly the kind of thing SETI scientists are seeking. Even the accidental noise of an alien culture would answer one of the most ancient questions of all.
Are we alone? Humans have been asking it forever. The probability of success is difficult to estimate. But if we never search, the chance of success is 0.
All right, so I want to show you. If you've never been to a planetarium before, what a planetarium is they take you through not just the planet, but usually the universe as well in some way, shape, or form. They usually have one primary goal. The one I've only ever been to, maybe 2. The one I remember most clearly is they kind of gave us scales. So they took us from Earth and then kind of like zoomed out and went to a distant galaxy, and they kind of really shows perspective. So what I want you to pay attention here is this is just giving you a tour of the universe in terms of perspective. So it gives you an idea of the Earth within our solar system, and our solar system within the galaxy, and our galaxy within the universe. All right, not what I wanted there. All right, so that gives you an idea of perspective there. So where we ended, I hope you're paying attention to the words as they went through there. All right, so here is another video on that observatory. I'm not going to show this one, but remember that telescopes that are on Earth are going to be limited by our atmosphere. So when we take a telescope and put it into space, we're able to not only see further because we're further away, but also we have less interference from the gases found within our atmosphere. Oop, push the button. Okay, so the Hubble was launched into space in 1990, and then they had to do a corrective mission. So basically, had to like reposition it in 1994. Now, this Hubble, if you wanted to check out the images that the Hubble has captured over time, they document it and have videos and talk about some of the stuff that the Hubble has captured. Some of my favorite images are when they compare the Hubble images to the James Webb images, because the James Webb has such a greater depth of imaging. Now, neither one of them are what the eye sees, what the naked eye would see, because we can only see visible light. Both the James Webb and the Hubble are able to capture just above and below by pulling infrared and X-ray, and they have different parts of those spectral ranges that they can pull and give you visuals for. So we'll focus a little bit more on some of these images tomorrow, as well as talking about some of the goals of the James Webb and how amateur astronomers through time have been able to capture things. What I want to leave you with is this is that image of Galileo that I was referring to, how he was able to just grab some supplies and make a telescope, not even knowing what it was, to have such an accurate image of what the moon looked like with its craters. And these craters formed long before we believe the moon was actually stuck in our orbit, and we'll talk about that as well later on. All right, that should be it for today.